Welcome back to the Dr. Liu VCE Physics channel. In this video, we'll go through the 2018 VCE Physics exam, focusing on questions related to light as a wave. My explanations may not be perfect, so if any teachers, parents, or students notice any errors, please feel free to offer your feedback. A loudspeaker produces sound waves, which are longitudinal waves. This causes a nearby dust particle to oscillate back and forth, moving in the same direction as the wave. According to the Doppler effect, the frequency of the siren sound increases as it moves toward Alex, causing him to perceive a higher pitch. Concurrently, the sound's amplitude also increases due to the decreasing distance, which makes the sound seem louder. The distance between adjacent dark bands is directly proportional to the light's wavelength and the distance between the slits and the screen, but inversely proportional to the slit separation. To increase the distance between adjacent dark bands, you can either increase the wavelength of the light used, increase the distance between the slits and the screen, decrease the slit separation. A wave is considered polarized when its oscillations are confined to a single plane that is perpendicular to the direction of the wave's travel. This can only happen with a transverse wave. The speed of a wave is equal to the product of its wavelength and frequency. This relationship, expressed as v equals f, can be rearranged to calculate the wavelength of the sound. When two speakers producing the same frequency are separated by a distance that is an integer multiple of wavelengths, the sound waves interfere to form a standing wave. Since the distance between the speakers, 10 m, is exactly 10 times the wavelength, 1 m, a standing wave is formed. The center point, which is equidistant from both speakers, is a point of constructive interference and is therefore a pressure antinode, loud region. The first quiet region, or node, occurs at 1/4 of a wavelength from the middle antinode. The next quiet region, the second node, is located half a wavelength further from the first node. Therefore, the total distance from the middle antinode to the second node is the frequency, f, of light is calculated by dividing the speed of light, c, by its wavelength, lambda, as shown in the formula. The critical angle is the specific angle of incidence, at which the angle of refraction is exactly 90 degrees. This causes the light ray to travel along the boundary between the two media. To calculate the critical angle for a boundary, such as between a cladding and a core, you use Snell's law by setting the angle of refraction to 90 degrees. For total internal reflection to occur, and a critical angle to exist, light must travel from a medium with a higher refractive index to one with a lower refractive index. This is because, according to Snell's law, the sine of the critical angle, sin, cannot be greater than 1. Therefore, n2 must be less than or equal to n1. The product of a medium's refractive index, n, and the speed of light in that medium, v, is a constant value, the speed of light in a vacuum, c. Using this relationship, we can establish the equation. We know that the refractive index of a vacuum is 1, and the speed of light in a vacuum is c.to. Calculate the speed of light traveling in a core. You can rearrange the equation to the laser's power output is 5.03 milliwatts, MW. To calculate the number of photons emitted per second, you can follow these steps. First, calculate the energy of a single photon using Planck's equation, which is E equals hf. The wavelength, lambda, is known. The equation can be written as follows: where c is the speed of light and h is Planck's constant in joule seconds. Next, divide the laser's total power output by the energy of a single photon. This will give you the number of photons produced per second. In the double-slit experiment, the middle band is always bright because the path difference between each slit to the middle is zero, which results in constructive interference at the middle point. At a point x, the path difference is 2.14 micrometers. This value is 3.5 times the wavelength of the light. Because it is a half-integer multiple of the wavelength, the waves interfere destructively, producing a dark fringe. Since the integer part is 3, this is the fourth dark fringe. This section, worth 20 marks, 15.3% of the total, summarizes key wave properties and phenomena, with a focus on light. Wave properties: only transverse waves, like electromagnetic waves, can be polarized. In contrast, longitudinal waves like sound cause particles to oscillate in the same direction as the wave. The Doppler effect explains why a siren's frequency and amplitude increase as it approaches. Interference and diffraction: in a double-slit experiment, the distance between fringes is directly proportional to the wavelength and screen distance, but inversely proportional to the slit separation. Two in-phase waves can form a standing wave, with loud antinodes and quiet nodes. Light and media: light's speed in a medium is its speed in a vacuum divided by the medium's refractive index. When light travels from a denser to a less dense medium, the critical angle is the specific angle of incidence, at which the light refracts at 90 degrees. Light as a particle: light also behaves as a particle, a photon. The energy of a single photon can be calculated using Planck's equation, and the total number of photons is found by dividing the power output by that energy. Should you require assistance, please feel free to connect via WeChat or WhatsApp and send an email. Thank you for your attention. Kindly note the details of Dr. Liu's VCE physics, chemistry, and biology channels.